Hello everyone. So welcome to IIT and Gate classes. So today we will be continuing our discussion on gas dynamics topic. So today's topic is quasi one-dimensional flows. So this is very interesting uh, physics we are going to see now. So till now whatever we discussed either one-dimensional flow field or in the oblique shock or the expansion waves, we discussed a kind of a two-dimensional flow field. So in today's session, we will be seeing about a very interesting assumption that is quasi one-dimensional flow. Where flow is actually a three-dimensional, but we are reducing it to a one-dimensional through an assumption, and we will analyze the flow physics through it. So that's what quasi one-dimensional flow all about. So we will see how governing equations and all other things looks like. So this is kind of a fundamentals required to go on to study the flow through ducts such as nozzles, diffusers, or wind tunnels, where both nozzles and diffusers are used. So to understand those flow physics, we have to understand first how quasi one-dimensional flow looks like, how a governing equations looks like, right? So let us start the session. So I am Akshay. So let us jump on to the uh, topic of interest. Okay. So first what I am going to do is, so I am going to start with a governing equation. First, let us compare what we know so far. So this is what we studied so far. One-dimensional flows in which area is constant. So it's kind of like the flow is going through a constant area duct or set of streamlines. So which you are interested in. So they are having a constant distance to each other. Of course, we are still treating it as a steady flow. And so this is the scenario we treated so far. So whereas all the properties are a function of the flow direction. So say in this condition, it's a function of x alone. Say flow is moving only in x direction. So then we will treat it as function of x alone, right? So now let us look at the figure B over here. So here, as you can see, here area is actually changing along the x direction, right? So here also we have drawn x, y, z Cartesian coordinate system in which along the x direction, as you can clearly see, the area is changing. Say at A1 over here to A2 over here, the area is clearly changed. A2 is greater than A1. And flow is going through like this. Say like set of streamlines, they are actually diverging or converging kind of thing. Okay. So like this. So they are changing their direction. So in this scenario, strictly speaking, this flow is three-dimensional. So wherever I take, so if I want to calculate velocity at this point, so the velocity is truly a tangent, right? So it has a component in x, y, and z direction, x, y, z direction. So truly speaking, it is a three-dimensional. But what we are imposing now is, so compared to x direction, the other two components, y and z components, are negligible. So we are treating it as a function of x alone. So that means area is changing in x direction. Similarly, any properties taken at any cross section in the x direction is going to be uniform. That means if I take a pressure, density, or temperature or velocity at any location, at a given x location, it is going to be constant. So that is a uniform flow. So this is the assumption we are going to impose. And we are going to see how my governing equations looks like, because in this scenario, note here, my area is not constant. So it is actually changing with respect to x direction. So my governing equation might not be same as what we have treated in one-dimensional flow. So that is we are going to see. whether it changes or it remains same. That's what we are going to see for a quasi one-dimensional flow. I suppose you guys understood the idea of quasi one-dimensional flow assumption. It's a very interesting assumption and very important consideration we have to do here, right? So in terms of analyzing the physics of a flow, so we are reducing our three-dimensionality into one-dimensionality, even though the area is changing along the flow direction. Straight and clear. So now what we are going to do is, so as simple as that. So we followed it multiple times now. So we are going to analyze it through control volume analysis. So let us try to draw a control volume enclosing this diverging or whatever this variable area duct, right? So see here, I have a control surface through which a flow is entering in x direction. So this is my x direction. So where properties are measured as u1, p1, t1 and area a1. And I have a surface 2 through which a flow is exiting. So in this control surface, if I measure the properties, they are u2, p2, t2 and a2. This area at the exit. So this control volume is denoted with stylish letter V, whatever it is, and a control surface is denoted with a letter S. So I have a tiny section of this control surface. If I take a differential section of this surface, so I am denoting it as ds. This is a unit normal vector for this small segment of the control surface. So remember here, I am treating this area to be a vector, right? So this is my unit normal vector to this area. So I can similarly I can draw at any section. So the unit normal vector. So here also I can just the representation purpose, right? So this is my control volume. So right now we will try to apply the conservation equation on this control volume. So again, the Reynolds transport theorem, we are going to utilize that idea. And my momentum equation or the, sorry, not the momentum. So my continuity equation, the mass conservation, it reduces to this form. So let us try to write it in nice and neat fashion. So what I have for an integral form of continuity equation is dou rho by dou t times volume integral of rho dv, the differential volume dv, plus closed contour integral of or surface integral of the flux term, that is rho, the velocity vector v dot the area vector s. So v dot ds. So as we are treating it is steady flow, so I can neglect this part. So this just comes out to be, which is equal to 0. The right hand side is 0. That we should not forget. So the control surface or the flux term associated with this one dot ds equal to 0. And as you can see here, I can write it in 3 terms, right? So this form. So one is at the entry, one is at the exit, and the integration from 1 to 2 in the surface. So if I write that one, so it becomes a surface integral. Sorry, not it is a contour. So I am dividing this contour into a different surfaces. So now at area 1, this is nothing but rho v ds, plus at area 2, this is again rho v ds, plus the area or the area integral in it is nothing but a double integral. So along the wall, right, it is again rho v ds. ds is again vector, right? So what we got now is at the entry, what is integration at the entry along that area 1? So that is going to be minus rho 1, the velocity is u1, v is equal to u in this case, times a1. This is negative because the velocity is in this direction, whereas my area vector in other direction. So u dot ds, that is a cos 180 degree, that is going to be -1. So rho1 u1 a1 plus at the exit, so I have rho2 u2 a2 plus along the wall I have double integral of along the wall rho v dot ds is equal to 0. And interestingly, you can see here, so this wall is in our physical sense, this is nothing but a streamline, right? This is one of the streamlines. So along this wall, whatever streamline you are considering, you see now my velocity vector and my area normal vector, they are 90 degrees to each other, right? So along the wall, what happens? My v dot ds is going to be 0 along the wall, right? So considering this factor, so this term actually vanishes. So I am left with minus rho1 u1 a1 plus rho2 u2 a2 is equal to 0. So that indeed implies that rho1 u1 a1 is equal to rho2 u2 a2. So this is my continuity equation for quasi one dimensional flows for a steady case, steady and inviscid case. Okay. Now we are going to analyze the momentum equation, and we have to note that the momentum equation is vector equation. It is not a scalar equation. So I have components of velocities along which I have to divide my equation. So considering it's a steady flow, what I am doing, so the steady part dou by dou t of volume integral that vanishes because of the steady assumption. So I am left with the integral equation is left with rho v dot ds times the velocity vector is equal to negative of, this is within the integration, so this negative comes within the integration, and surface or closed contour integral of p times ds. This is a vector again. So now what I am doing, so I am writing a respective component, so that is a x momentum equation. The x momentum equation turns out to be this component velocity v has u, v and w in three-dimensional space. So the x direction or the x component of velocity is u. So this is the flux term. This one I am not writing in terms of the component wise. So I am still keeping it as v dot ds, whereas this defines the direction, right? So this is x momentum. So this u I am keeping because it's the x momentum along the x direction. So the right hand side, the pds, this subscript x denotes the pds is taken along the x direction, right? So this is my x momentum equation in integral form. So now we have to look this very carefully, especially the right hand side. The left hand side is straight and clear now. I have rho v dot ds times u. So I can write, because it's assumed to be quasi one dimensional, that means my velocities in v and w direction is negligible. So v basically becomes u in the x direction, say in ix or I cap, right? So v becomes u alone. So it becomes rho u times a, that is v dot ds is ua, and depending on the sign, whether velocity vector and area vector are pointing parallel or anti-parallel, so this becomes negative or positive. So in the inlet, I have u is pointing this direction and a is pointing this direction. So definitely there is 180 degree difference between the direction difference in those two vectors. So I have negative sign in front of that. Rho1 u1 square. Why it is u1 square? Because this u and this u are multiplying now. So rho1 u1 square times a1 plus rho2 u2 square times a2. So this is my left hand side. And upper and lower surfaces, again, as we discussed earlier, so along the surface, what we have, so this surface and this surface, upper and lower surfaces, so that is again streamline. So velocity vector as well as the area vector are 90 degrees to each other, so it vanishes. So we left with only at the entry and at the exit. So this surface and this surface contribution vanishes because of v dot ds is 0, right? So it is already within the integral. So integrand is 0 means integral also 0. So it vanishes. So now we look at the right hand side. So that is the pressure part, right? So what we have in the right hand side, minus contour integral of PDS in the x direction, right? So now again, if you look at this part very carefully, what we have is, it can be divided into three parts again, right? It's a contour integral. So what I can do is negative of A1 P ds in the x direction plus, let me keep like this, integral A2 P ds in the x direction plus integral along the wall, right? Wall, that is PDS in the x. So these two parts are straight and clear. Pressure is acting this way and area is acting this way, but pressure is a scalar quantity. It is not a vectorial quantity. So there is no meaning if I now take the direction corresponding to these two, because this is already a scalar. It's no more a vector PDS. It's a scalar, right? It's already taken a component, right, in the x direction. So it's now a scalar. So now what I left is, if I integrate this one, it becomes P1A1 plus P2A2, but this is negative because area is pointing the other way. So this negative is already there outside, minus P1A1 plus P2A2 minus of integration of, again that minus is already there, minus PdA. So ds I am writing it as dA, going from A1 to A2, right? So A1 to A2. So this part I cannot neglect now, because the pressure is changing between A1 to A2, and that one I have to consider because the area is already changing. So I have to account for that, right? So this part becomes A1 to A2 PdA, and negative of negative becomes positive. That is my right hand side. And along the wall, what happens? Along the wall, again, similar conclusion. Because I have upper surface and the lower surface, the pressure is acting everywhere uniformly from the atmosphere. So whatever acting over here, the opposite kind of pressure is acting on the upper surface. So the net part is going to be 0. So that part we are not going to treat. So we are only treating what is happening in the x direction from A1 to A2, and what is happening at A1 and what is happening at A2. So we are not concerned about this direction, other direction. So they are going to vanish. Okay. So my momentum equation somewhat looks like this now. Rho left hand side, rho 1 u1 square a1, rho 2 u2 square a2. Right hand side, negative of negative p1 a1 plus p2 a2 plus a1 to a2 pda. So now if I take the like terms one side, so it becomes p1 a1 plus rho 1 u1 square a1 plus pda is equal to p2 a2 plus rho 2 u2 square times a2. This is momentum equation for a steady quasi one-dimensional flow. Okay, so now let us move on to energy equation. This is again a quite straightforward. Again, it's a scalar equation. So rho times E plus V square by 2 times V dot ds is equal to, again, the surface integral, because volume integral comes with dou by dou t, and we are assuming it to be a steady process. So steady flow. So that part vanishes because of steady assumption. So now right hand side is negative times as closed contour integral of P times V dot ds, flux term. So now both the side we have flux term now. So straightforward we can apply. So V dot ds is nothing but U1 A1 minus U1 A1 in the inlet, and plus U2 A2 in the outlet. So that's what I am writing here. Rho 1 times U1 plus U1, V becomes U now. because quasi one dimensional assumption u1 square by 2 times minus u1 a1. So similarly, right hand side becomes p1 u1 a1 and negative of negative plus p2 u2 a2. So again, we are keeping the like terms one side, and the um, uh, left hand side and right hand side becomes a function of inlet and function of outlet. So now what I'm going to do is I'm going to divide this equation by continuity. So this result we already obtained for quasi one dimensional flows. So if I divide this equation by continuity, what happens in this term? U1 A1 cancels, U1 A1 cancels, this side U2 A2 cancels, U2 A2 cancels. So I am left with P1 by rho 1 plus E1 plus U1 square by 2. So rho 1 U1 A1 cancels, rho 2 U2 A2 cancels, U2 U2 cancels, U1 A1 cancels. So I am left with P1 by rho 1 plus E1 plus U1 square by 2 is equal to P2 by rho 2 plus E2 plus U2 square by 2. What is this one? P1 by rho 1 plus E1. This is coming from our thermodynamics idea, right? Enthalpy is nothing but internal energy plus flow work, P V, or I can even write P by rho. So that's V is nothing but 1 by it's a specific volume, so it is nothing but 1 by density. So E plus P by rho is nothing but enthalpy. So it basically becomes H1 plus U1 square by 2 is equal to H2 plus U2 square by 2. So this is a well-known form of energy equation. We already saw multiple times. So even for quasi one-dimensional flow, it looks like this only. So it implies that in quasi one-dimensional flow with an inviscid and steady assumption, and also it's an adiabatic. So H naught is constant. Even further, if I treat it as calorically perfect gas, I can show that it is T naught is also constant. Okay. Straightforward. So right now, what we got is all the governing equation in the integral form of equation for quasi one-dimensional flow with steady, inviscid, and adiabatic assumption. So now, in theory, we can actually solve for a given flow field if I have these governing equation plus I have two thermodynamic variables. So thermodynamic equation, that is a equation of state P is equal to rho RT and H is equal to CPT or E is equal to CVT, whatever. So from these 5 equations, I can solve for all the unknowns I know, given that I know the function area as a area function of X. So if I know this one extra and all other variables, I can actually go on to calculate. In theory, practically it becomes really difficult because it involves a lot of algebraic manipulation. So for that one, what we can do is, so we will try to understand what this equation tells us, what this equation physically means. So to address that one, what I am going to do is I slightly deviate from this part of the equation, that's the integral part of the governing equation, and I will try to look the same equation from the differential form. So we know, like for any given fluid mechanics problem, we can either write in conservative form or non-conservative form. Even in conservative or non-conservative, we can still go on to write in integral form or differential form, right? So all of them basically represent same fluid flow physics. So we can also represent the similar governing equation in differential form. That's what we are going to see now. So that's what we are going to see now. So the continuity equation says me that rho 1 u1 a1 is equal to rho 2 u2 a2. So what does this mean? So this means that rho ua is equal to constant, right? So from here I can easily construct a differential equation. So if rho ua is constant, that means a differential of rho ua is 0, right? So if I integrate this one with respect to rho ua, I get rho UA is equal to constant. I can expand this equation further. What I can do is, so it's a variable separation again. So I have rho U times dA plus I can write rho A times du plus AU times d rho equal to 0. And again, if I divide it by rho UA, I will call it as equation 1. And again, if I divide it by rho UA, so it becomes like dA by A plus du by U plus d rho by rho is equal to 0. So it's again the different forms of same equation, right? It's nothing fancy over here. It's just the different forms of the same equation. We are just algebraically manipulating it. That's it. So let us call it as equation 2. So these different forms of governing differential equation. Okay. So now we go on to see the differential form of momentum equation. This is a bit tricky over here because we cannot directly do what we did like in continuity equation. But what I am going to do is like instead of treating the whole control volume, I am going to treat a differential control volume, the small volume with the distance dx, right? Within this, the area is changing by a plus dA, and pressure is changing by 3 plus dP, velocity is changing u plus du, rho density is changing rho plus dou rho, like that. So it's in the differential volume, the quantities which are going to change is also differential. So the small quantity or the small amount is going to change within that small distance through which a flow is traversed. So that's how we are going to construct the differential equation, and we are going to apply between point 1 and 2. So we already had P1 A1 plus rho 1 U1 square plus times A1 plus integration of PdA from A1 to A2, like that, right? So this is what we are going to do. So here in the left hand side, if I apply, this is PA plus rho U square A plus PdA. So this is integration of PdA from A1 to A2. Considering A1 to A2 is not going to change a lot, so I am just taking out this integral, and I am writing it as PdA as it is, right? So the right hand side is all the quantities are changed by P plus dP, like A plus dA, rho plus dou rho, like that. So the right hand side also I am writing, instead of P2, I am writing P plus dP. Instead of A2, I am writing A plus dA. Instead of rho 2, I am writing rho plus d rho. Similarly, instead of U2, I am writing U plus du. That's what I am doing here, from integral to differential. So now, if I expand this, right? So the right hand side, so left hand side, nothing to expand. So in the right hand side, I can expand this, right? So if I multiply like this, PA plus PdA plus AdP plus dPdA plus, let us keep this as it is. First multiply these two. So I get rho A plus rho dA plus A d rho plus dA d rho plus, times this one. I am expanding A plus B whole square, U square plus du square plus 2u du. Fine. So now what I am doing is I am treating the higher order differential terms to be 0. That means like whenever I see a two differential which are multiplied, so I am going to treat it as 0, because the smaller quantity multiplied with another smaller quantity becomes even smaller quantity, right? So that is why I am going to treat this to be 0. Similarly, du square going to be 0, and I have dA d rho. This is going to be 0. This is all multiplying to this. Where was this? This one, right? So this is going to be 0. So now what I am left is, in the right hand side, equal to PA plus PdA plus AdP plus multiply rho A times U square, that becomes rho U square A plus rho A times 2u du. So that becomes 2 rho u du dA plus I have this also 2 u rho A times du, 2 rho u A times du plus rho dA times u square, that is rho u square times dA plus A is multiplying with this one, A d rho times u square, that is A u square times d rho plus A 2u times du rho, that is 2 u A times d rho du, right? So again, the same argument, the higher order terms, whichever having the two differentials multiplying each other, I am going to neglect the du dA 0. I have again d rho du going to be 0. What I am left is in the right hand side, I am left with PA plus PDA plus ADP plus rho u square A plus 2 rho u ADA, sorry, A du plus rho u square dA plus A u square d rho, right? So this is what I am left with. So now right hand side I already have PA plus rho u square A plus PDA. So now from left hand side and right hand side I can cancel PA rho u square A rho u square A PDA. So this cancels out. So what I am left is now ADP plus 2 rho u A du plus rho u square dA plus A u square d rho, which is equal to 0. The left hand side is already 0. So this is what I left with. So this is the same thing I have written over here. ADP plus A u square d rho plus rho u square dA plus 2 rho u A times du equal to 0. Now, if you look back, we had this form, right? 1. So now to 1, if I multiply u, 1 into u, so what it becomes? It becomes rho u square dA plus rho u A du plus A u square d rho equal to 0. So now let us call it as equation 3, and from equation 3, and this is my equation 4. So now if I do equation 4 minus equation 3, what I am left with? So I had equation 3, that is, what did we have in equation 3? Equation 4 minus equation 3 I am going to do now. So in equation 4 I had A dP plus 2 rho u A du plus rho u square dA plus A u square d rho, and equation 3, in equation 3 I had minus, right? I'm going to subtract it. So A u square d rho minus A u square d sorry, rho u square dA minus rho UA dU, right? So right hand side is equal to 0. So now you see here, A u square d rho, A u square d rho cancels out. Rho u square dA, rho u square dA cancels out. I have 2 times rho UA dU minus rho UA dU. That leads to AdP plus 2 rho u, sorry, 2 minus 1 is 1 rho UA dU equal to 0. So both the side I can cancel out A, right? A gets cancelled. I left with dP is equal to minus rho U du. So it should ring a bell. It is nothing but Euler equation for inviscid flows, right? It's nothing but an Euler equation for steady and inviscid flow. So it is expected, it is not a surprise actually, it's expected for an inviscid flow, we should end up with Euler equation only, right? But the important point here is like we did not assume it to be an Euler equation in the beginning. We started with whatever governing equation we had and we ended up getting Euler equation at the end, right? So it is important, the momentum equation whatever we got now. So now the energy equation, again the differential form is easy. dH plus u du is equal to 0 because h plus u square by 2 is constant. That means dH plus u du is equal to 0. That's the differential form, right? So now we got the differential form as well as the integral form. And I told you in the beginning why we need the differential form, because I am trying to come to a point where we can explain the physics which is involved in these kind of flows. So to understand that one, so we are again looking deeply into this differential form of the governing equation. So the continuity equation, whatever I had, so I told, so I can also express in this form, right? So I had in this form. So from here, what I'm going to do is, I'm going to change this d rho by rho in terms of these variables, whatever I already have. So how we can do is, so d rho by rho can be written in terms of d rho by dp times dp by rho, right? But what is this one? Because pressure is a function of rho and u both, so area also. So I can easily write a density change as a function of pressure. So that's what I'm doing now. And from the momentum equation, what we had, dP is equal to minus rho u du, right? So dP by rho can be written in terms of minus u du. So I am replacing over here dP by rho. So that is nothing but my d rho by rho can be written in terms of d rho by dP times dP by rho, that is minus u du, right? So now I am imposing one more condition. Till now we just imposed adiabatic assumption. Now I am imposing it is also a reversible. That means like I am assuming there is no shock or those kind of things exist within the flow field. So adiabatic plus reversible. So that means isentropic assumption I am actually going to take for this kind of flow field. So the moment when I take it's an isentropic flow field. So what happens? We know for isentropic flow field dP by d rho. So equally I can write in terms of dou P by dou rho with S being constant. So what is this one? This is nothing but speed of sound squared, right? So this we already derived while discussing the speed of sound. So I can replace dP by d rho in terms of a square So this becomes d rho by rho is nothing but minus u du times 1 by a square, right? So now you see dp by d rho, I am replacing it as a square. So that becomes dp d rho by rho is minus u du times 1 by a square. So now looking back my equation, that is d rho by rho plus du by u plus dA by a from continuity. So I am replacing d rho by rho in terms of this equation, that is minus u by a square times du plus du by u plus dA by a. So now we got rid of this one more term. So we express only in terms of u and a. So this reduced. So now I am just multiplying and dividing by u into this term. So that becomes minus u square by a square times du by u plus du by u plus dA by a equal to 0. So now take du by u terms to other side and keep dA by a this side. So this becomes dA by a equal to du by u, I am taking common, that becomes u square by a square. What is u by a? That is Mach number. So m square minus 1. Very important relation we actually got now. This is referred as area velocity relation, not area Mach number. It's an area velocity relation. So this says me for a differential change in area, how does my differential change in velocity looks like if my Mach number is less than 1 or if my Mach number is greater than 1. Look this very carefully. Say like I have Mach number which is greater than 1. So if Mach number is greater than 1, what is this quantity? M square minus 1 is positive, right? So this becomes dA by a is equal to some positive number times du by u, right? So for a change in area, I am expecting similar change in velocity. That means if area is, say, my area is decreasing, converging, right? So I have A1 and I have A2. What is dA now? dA is A2 minus A1 is dA. So dA is negative for converging duct, right? So dA is negative. That means to make this positive, du also has to be negative, right? So then only you can expect this term to be positive. So that means in a converging duct, if m is greater than 1, right? So now if area is decreasing, that means dA by a is, this is negative divided by a equal to positive times du by u. So the entire equation becomes negative because the left hand side is negative because area is decreasing, dA is negative. So that means du has to be negative, right? To make this left hand side negative. So that means du has to be negative. So that means u2 minus u1 has to be less than 0 or u2 has to be less than u1. What does this say? u2 has to decrease. That means flow has to decelerate from this point to this point if m is greater than 1 at point 1. So in a converging duct, if m is greater than 1 at the beginning, that means it is going to decrease for a supersonic flow. So say for the similar argument for the diverging duct, if I have the diverging duct, so what happens now? So I have A1 over here. Let me change the color. So I have A1 over here. I have A2 over here. So my dA is now positive, right? dA is positive. A2 is greater than A1. dA is positive. So that becomes positive divided by A is equal to m is already greater than 1. That is what we are treating now. So for supersonic entry, m is greater than 1. So m square minus 1 is positive times du by u. So if this is positive, that means du has to be positive to make this left hand side positive. That means if du is positive, that means u2 minus u1 is greater than 0 or u2 is greater than u1. So what does this say? So in a diverging duct, if the inlet condition is supersonic, that means the flow is going to accelerate, right? So you can also do the similar argument for the subsonic case and when m is less than 1. So if m is less than 1, what happens? I have dA by A equal to m square minus 1 times du by u. If m is less than 1, if m is less than 1, so this quantity becomes negative, right? So this becomes dA by A equal to negative number times du by u. So now treat the similar scenario. M is less than 1. I have a converging duct now. So I have an area which is decreasing. That means A2, A1, A2 minus A1 or dA is A2 minus A1, which is negative. So this equation becomes negative divided by A equal to, this is already negative because Mach number is subsonic. So du by u. If this is negative, this is already a negative. So to make this part negative, so this has to be positive. If this becomes negative, then negative of negative becomes positive. It is not a valid condition, right? So to make this is negative, so this has to be positive now. Du has to be positive. So that means du needs to be positive. So that means u2 minus u1 has to be greater than 0 or u2 has to be greater than u1. So for a subsonic case, in a converging duct, it accelerates. So u increases or velocity increases. Similarly, if it sees the diverging duct, so then u becomes or u decreases. So same argument you can do. So this gives you a very interesting physical insight for a flow through a duct, which is supersonic or subsonic. So depending on the inlet conditions, you can actually comment whether flow is going to accelerate or decelerate given the inlet condition, right? So that is why this differential form of equation was very, very helpful to understand this flow physics in our case. So now we understood to make flow to accelerate from subsonic to supersonic, what do we need? We need first a converging duct through which a subsonic flow accelerates, and so at some point it reaches to a sonic condition and then it has to accelerate further. So then I have to give, like, because now we are going into the supersonic regime, then to accelerate further I have to change the area. That means area now has to diverge. So that is why my supersonic nozzle, which actually makes subsonic flow at the entry to a supersonic flow at the exit, that has to be converging and diverging duct. Only converging duct cannot create a supersonic flow because that max it can reach m is equal to 1, because we already saw from our equation, right? So dA by A equal to m square minus 1 times du by u. So the condition when m becomes 1, dA by A becomes 0 because m is equal to 1. This part becomes 0. It becomes a physically impossible situation to deal with in this mathematical term. So for that we have to look in the other way. So how we can address this issue. But the only condition through which we can achieve is converging duct through which flow accelerates from subsonic to a sonic. Then it becomes a sonic. Then we have to see a further acceleration. For that it has to reach a supersonic. To make that supersonic, I have to have a diverging duct as dictated by my area velocity relation. So converging diverging duct can create a supersonic flow from low subsonic to supersonic. Similarly, if I want to have a diffuser, again the same argument, diffuser is a duct through which a flow decelerates, right? Again, if I have a supersonic flow at the entry, if I want to make it subsonic at the exit, the same scenario occurs. So it has to decelerate through a converging duct because for a supersonic flow, the converging duct makes it decelerate, flow to decelerate, then it sees somewhere in the throat, it becomes sonic, then again it has to decelerate to subsonic. For that, again, I have to give a diverging duct, because in subsonic regime, I want a diverging duct to make flow decelerate. It's a very interesting flow physics, which actually through which we are seeing a number of applications, right? Like even in wind tunnels or in the aircraft or rockets. So whenever we want a supersonic exit, we will have a converging diverging duct. Why? Because that is how physics told us. So because of that only we designed this and it's working, right? These are all purely dictated by physics, but yet we can see the applications, right? So which are actually working, through which supersonic aircrafts are flying, or rockets are flying out of the atmosphere, or wind tunnels are working fine. So these are very intriguing concepts in terms of gas dynamics, through which like we can actually achieve the things which we can achieve, right? So as an engineering perspective, these are all like wonders what we have done so far, right? Okay, so I will leave you at this point, and I have a proof for thought. How does area velocity relation behave when flow approaches a low subsonic speed, such as incompressible limits? It's a very, very interesting question. What is an incompressible limit? So when Mach number approaches 0, right? How does my area velocity relation looks like when it reaches incompressible limits? It's a very interesting thought experiment you can do, right? It has to valid, right? So if m approaches 0, look at this equation. What it becomes, dA by A is equal to m square minus 1 times du by u. So if m approaches 0 in the limit of the incompressible flows, it becomes just dA by A is equal to minus du by u. What does it say? What does this say? It just says A into u is constant, right? It's a very familiar result, right? What is this? It is nothing but a volume flow rate is constant, right? Because density is already constant for incompressible limits. So instead of my entire mass flow rate, so I will treat A into u is constant. That's the volume flow rate is constant. That's an incompressible limit for continuity equation. Very interesting result. We can actually show that from this point also, right? So these are the things you guys have to think beyond what is given in the textbook, right? Okay, so I will leave you at this point, and we will take a few questions from previous year gate. Okay. Okay, the question one is, for a quasi one-dimensional isentropic supersonic flow through a diverging duct, which of the following is true in the direction of the flow? Very simple and straightforward. So they are given both Mach number and static temperature increases. The Mach number increases and the static temperature decreases. The Mach number decreases and static temperature increases. Both the Mach number and the static temperature decreases. So how do you going to answer this? Because it's an isentropic flow field, you have to remember that. So in an isentropic flow field, even for adiabatic flow field, I can write T naught is constant, considering it is calorically perfect gas, and they are given the diverging duct through which a supersonic flow is entering. M is greater than 1. Okay, so if it is diverging duct, that means if M is greater than 1, when it sees the diverging duct, what happens? M goes on to increase, right? M increases in a diverging duct, right? So that we just saw. So now, if M increases, what happens to temperature? This is where you have to think. I have an isentropic relation or even adiabatic relation that relates my Mach number 1 plus gamma minus 1 by 2 times m square. Straightforward from energy equation. So now I can write for static temperature T is equal to T naught divided by 1 plus gamma minus 1 by 2 times m square. Given that calorically perfect gas, gamma is not going to change, it's constant. T naught is constant because it's adiabatic flow field or isentropic, it is already stated in the question. So only variable which is changing is Mach number. So in diverging duct, if it is supersonic at the entry, we know M increases. If M increases, what happens to T? T has to decrease, right? So the static temperature decreases, Mach number increases. Which of the given option is correct? Option B. The Mach number increases and static temperature decreases. So option B is correct. Okay. So now let us look at the another question. Consider one-dimensional isentropic flow at a Mach number of 0.5. If the area of cross-section of a stream tube is increased by 3% somewhere along the flow, the corresponding percentage change in the density is. It's the same idea of quasi one-dimensional flow. They are given in the statement. So you have to understand. So though they are saying it's one-dimensional flow, but area is changing. The moment when they say there is a cross-section area which is changing, you have to make sure one-dimensional assumption with area changing. Immediately you have to approach the quasi one-dimensional assumption and proceed. So from the given question, say like I have a stream tube like this. So these are all the streamlines. What is stream tube? Stream tube is just a set of streamlines which is passing through a volume, right? So this is my stream tube. All are my streamlines. Okay, so what they are saying, I have A1 somewhere over here and A2 somewhere over here. Somewhere in the stream tube, the area is changed by a 3%. So that means dA by A is 3%, or I can write 0.003. That is 3%, right? 3 by 100. So this is what they are given in the question. And what is my Mach number of the flow? M is 0.5. So if M is 0.5, that means it's a compressible limit still. So I can approach this quasi one-dimensional flow for inviscid flows because it's isentropic flow. So I can easily take this idea of quasi one-dimensional continuity equation, that is d rho by rho plus dA by A plus du by U equal to 0. So now you see they are asked to calculate the percentage change in density. So we are not replacing this part now. So they are already given dA by A. So this is known quantity. So what I have to do is this du by U, I have to make sure to convert either of these two so that I can easily solve this equation, right? So how we can do that? I have du by U and I have area velocity relation. So that says me dA by A is equal to m square minus 1 times du by U. And this is already known. M is already known. So I can easily write du by U in terms of dA by A and known Mach number, right? So I can write du by U equal to dA by A times 1 divided by m square minus 1. Right? So now I am replacing that one over here. So this becomes d rho by rho plus dA by A plus dA by A times 1 by m square minus 1 equal to 0, or if I shift everything to other side, so because d rho by rho, which is I am interested in, so this becomes minus of dA by A, I am taking common, so that becomes 1 plus 1 divided by m square minus 1. So what is this one? If I take the LCM, so minus dA by A times m square minus 1 plus 1 divided by m square minus 1. So 1 get cancels. It becomes minus dA by A times m square divided by m square minus 1. Right. So now if I take this negative inside, so I can write in terms of dA by A times m square divided by 1 minus m square. So this is just to get rid of that negative sign. So this is equal to d rho by rho. This is what we want to calculate. So now put the numbers which is given in the problem. dA by A is, dA by A is 3%. So I can write d rho by rho equal to 0.003 times m is 0.5 square divided by 1 minus 0.5 square, right? So what is this one? 0.003 times 1 by 4 divided by 1 minus 1 by 4. So if I take the LCM again, 0.003 times 1 divided by 4 minus 1 is 3 by 4. So 4 get cancels. I get with 0.003 divided by 3, that is nothing but 0.001. That means 1% change in density I can see, right? So the change in density is 1%. So that's what they are asking you to calculate. Percentage change. So you make sure to write it is 1%, not 0.001. That is the fractional value, but percentage is 1%. So for 3% change in area, I am going to expect 1% change in density for given Mach number of 0.5. So that concludes our discussion on quasi one-dimensional flows. In the next class, we are going to study in the next session, I am going to introduce you the flow through nozzles and diffusers or wind tunnels, like those concepts, which basically coming out of this quasi one-dimensional flow funda. So we are going to see in the next session that. So thank you for listening, and for more information, you guys can contact us in iitiansgateclasses. So thank you.